Okay, let's begin. So today I want to recap what Sierra told you on Friday, and I think it's a really important problem, and I'm not surprised, but I'm dumbfounded that people don't know this problem. And so this is a very big statistical deal. It might be the biggest analysis, the most common analysis that people do, and not understanding the repercussions is just poor science. And so I don't think it's your fault. I think it's just maybe it's the Statistical Association's fault. So not telling people that we need to teach this differently. They've had commissions. I can tell you what the papers say in the commissions, no agreement on what to do, what to proceed with, all the same anecdotes as before. And so, but I'm going to tell you that this is a big deal, and we need to come up with something if we're going to have any success in using these sort of testing methodologies to advance science. So this is a pretty common problem where I have two samples. So I've got two samples up here, and I've made this really simple. I've said those samples come from a normal distribution. So that might already be a little bit like of an oversimplification. The real problem concerns when you don't even know what these distributions are, but we still use X bar and Y bar to test. And so central limit theorem does something for us. And so there's a little bit of a difference that what I'm writing down is that when I have normality right here, I get normality in this particular case. I'll go through the cases in a moment, and this is an absolute t distribution. If these aren't normally distributed, then these eventually hold. So it's an asymptotic result. What I mean by eventually is not in your lifetime, or ever really, when I have an infinite number of data points. And if I had an infinite number of data points, I don't need to test anything, because I know the truth. So, but saying that, these become almost true, and maybe we can use them. But almost always worries me. And so I do like asymptotics. I do like taking limits and seeing what the limit of thinking is, but I think this is a thinking exercise. I don't think it's stuff that we should necessarily use in practice. If approximations are good, then okay, let's use them. But we have to define good. How do we ever know if a mathematical approximation is good? How would you know?
Reflects reality.
Reflects reality. Who knows? Maybe you bury yourself in a cave. The allegories come to you and you know what the truth is. So maybe the old philosopher's wisdom. What do I do to check the truth?
Simulation.
I go to simulation. And so every single time. And so at least I can encode what a true model is and use that exact model and see what happens case by case. I can usually do it in like 20, 30 minutes if the problem's simple enough. A typical exercise that we'd see in first couple years of grad school, not anything totally horrendous. That would take longer. But I could check all these basic results that we learned in inference class using my computer real quickly, and then I could teach myself how to do the math. And so, and I could see what the repercussions are. So I could check all these results using a simulator, and we will in a moment. So, a little bit of a simplification here with normality, and I could change those to different distributions pretty easily. And I could build in distributions with interesting properties and maybe contain classes of distributions. See what happens kind of in general. Not really, but maybe close enough for my thinking that I can go on and now do my math and understand what I'm supposed to do.
So, excuse me, so you're saying if this was not normal, we would be testing on X bar, and to the limit, things would be going to and t.
That's right.
But what do we do if it's not to the limit? I mean, you're saying that if we have infinite data, then we wouldn't have done that.
I'm just saying maybe the central limit theorem is a good result. We know that X bar tends to something normal. It never quite gets there, but it tends to some normal, and we use that result all the time.
And if we do know the distributions, but let's say they are gammas or t's, or I don't know, would we also test on X bar and use the central limit theorem? Or would we
Depends on which t you got. So if you've got a t1, I wouldn't be using any average. So if averages existed, that's the typical 1960s statistician trick, is compare means. Why do we compare means? Because we've got central limit theorem. And so why do we compare means in additive fashions? And so that's actually usually, that comes out of Neyman Pearson that tells us maybe we should do that. It's the most powerful way to test the difference. We could have tested in ratios. Does anybody know what a normal over a normal is?
Uniform.
It's not uniform. It can't be uniform. So it's Cauchy. Yeah, it's kind of interesting. So anyway, we do it because the central limit theorem, if the central limit theorem kind of works for us. What are we testing? We're testing averages. That's pretty limited, right? Is the mean the same? That doesn't mean the distribution is the same. But that's one way of going about business. So this is just Stat 101. If you take a Stat 101 class, this is the whole class, bless you. This is the whole thing, what I have on the board. That's Stat 101. And so you learn all the variants of a t-test. They first teach you the z-test, then they teach you t-testing, and they might teach you what a mean, median, and mode is. It's about like that. They teach you some properties of these things, but if you understand all this, you've taken Stat 101. Right, Quinn? About it. You've taught these classes, right? No, not yet. You've taken them. Okay, well, we'll trust that what I just said is true. Okay, so case one, and maybe these are asymptotic results, but if I plug in normality right here, these are absolute results. And so this is true. And so you could check this almost instantaneously. And so this is, we know what the distribution of x bar is, we know what the distribution of y bar is, we know what the distribution of the difference is. And so hopefully you know that, and you could actually do this in like a second. So that one's really easy to walk through. So no problem. Bayesians also will use this sort of result. They'll put a prior on maybe this. They'll put a prior probably on mu x and mu y, flat priors, and they'll invert this thing. And so the classicist, or whoever they are that's using that result, the Bayesian's very similar to. And so we'll use a distribution or form just like this. So of course, if I put a flat prior on this, if I know these things, I'm going to get a distribution on the difference here, and it's going to be centered here. So I'm just going to change those around, do that flip, that conditional flip. And so Bayesian will use this distribution. Their interpretations of all their analyses are a little bit different. Coverage versus confidence. So, and sharp testing, there'll be an absolute difference between what a Bayesian and a non-Bayesian do. For one-sided testing, we'll have very similar results. In one-sided testing, under a flat prior, the Bayesian's posterior probability is going to be the non-Bayesian p-value. So, this case is pretty easy to handle as well. And so if these are both equal to each other, but they're unknown, then the typical result is this, where this is a pooled variance right here. So I end up taking my variance estimator for sigma x squared hat. I look at n minus 1 plus m minus 1 sigma hat y squared, and then I divide by the sum of those two things. So n plus m minus 2, and that's the degrees of freedom that we end up getting right here. N plus m minus 2. And Sierra wrote some integrals on the board. And a Bayesian, if they ended up putting a prior on 1 over sigma x squared is equal to 1 over sigma y squared, and I ended up just calling this phi. If I ended up using p phi proportional to 1 over phi, the typical Jeffreys prior, then the results that the classicists have using this distribution and what the Bayesian get are going to be very similar, i.e. these things are going to interchange. So the conditional flip, but this variance form will be exactly the same. And if you just go through the integral, you know, looking at the gamma kernel and doing all that stuff and keeping track of all terms, this is the exact same result. So Bayesians and classicists use the same distribution in case 1 and 2. And there's no approximations. These are just known results, pretty standard Stat 101 stuff. I would encourage you, go through, see if you can actually do that integral yourself. Again, it's all the same collection of techniques that we've done before. This one you should be able to do in your head. This is where all the contention arises, right here, this case. And this is actually called the Behrens-Fisher problem right here. Behrens-Fisher. So these cases, no problem. So this case, however, big problem. And what do we do? So a lot of people will base it off of this distribution, and in Stat 101 you learn that this thing has that distribution. And there might be a very small footnote disclaimer. I never read it in any of my Stat 101 books. And I don't know if it's there in well over 90% of them. But this result is not true. This is false. So let me just write this down.
What does the footnote say?
False. This is not true. So somebody tell me, where's the statistical error? Where's the statistical crime in all of this? What's the assumption? So here's what happens. In this case, we had n plus m minus 2. If I ended up plugging in the same thing right here, that I estimated both these things using x bar and y bar, the degrees of freedom maybe should have been n plus m minus 2. But they end up correcting this thing, and this is called a Welch-Satterthwaite correction. And really, if you don't know that, I'm really scared for science.
It's not a t, so they're just assuming that it's a t.
That's right. Why is it not a t? This is not true. It's not even true asymptotically. What does a t-statistic look like? What does a t-distribution look like in terms of a mixture between a chi-squared and a normal? So t's.
Should be a normal divided by the chi-squared.
Is it? So it's a normal 0, 1. Right? Divided by square root. Chi-squared with some number of degrees of freedom. Divided by the degrees of freedom. Okay, so that's what a t-density looks like. Here's a statistic. So I'm going to look at x bar minus mu naught over sigma naught. You can divide by n. I'm going to say this is the standard error for x bar. Okay, so that's my sigma. Typically it'd be sigma squared over n. That's the standard error for x bar, where sigma squared is the standard deviation for each xi. I don't care what you call them, they're both standard deviations, it's just one is over a statistic. So that's normal 0, 1. Then we end up looking at this creature usually. Square root sum of the xi's minus x bar squared over sigma naught. This thing is a scaled chi-squared. If these aren't 0, 1s right here, then I've got a problem. They're zeros, but they're not scaled right, so I have to scale them right here. I scale them in the squared sense, and I divide by n minus 1 right here. These two things cancel each other. If you've never seen that, you don't know why you're using this statistic. So those two scale factors end up canceling each other, and this is the typical statistic that we use in a t-test. And so I'm constructing this result, just using this typical sort of statistic. So here's the statistical culprit, is that these things right in here in this sum need to be IID. They're normally distributed, asymptotically normal will do it. But if they're normally distributed in IID, then I can add them all up and this thing is chi-squared. But when I end up doing the same thing over here and I'm adding together these two functions, they look like this. There's a corresponding one using the y's. So this thing is just sum of the yi's minus y bar squared m minus 1. When I add these things together, they came from two not identical processes. That's not chi-squared. So when you form this statistic and you add these two things together, that's not t.
Shouldn't they be sigma squared x and sigma squared y?
Okay. Yeah. Thank you. So all that goofy stuff we do on the board. Couldn't understand why my instructors would make these mistakes. It's like, you're well trained. I do it all the time too. So, but yes. So when I add those two things together, that thing is not a chi-squared. It's not a scaled chi-squared. It's something different because it came from two not identical processes. I don't know what the distribution is. And so I could probably figure it out for certain cases. If I could probably even write it down for particular cases, probably changes to weird stuff. So saying that, so when I form that sort of statistic and I try to t-test using it, it's not a t-distribution. That's the Variance-Fisher problem. Do you know what distribution this statistic would follow? So if I ended up looking at x bar minus y bar over square root sigma x squared over n plus sigma hat y squared over m. Do you know what distribution this would actually follow in this case? Do you know what it's called?
This is the second one?
What's that?
The second one.
It's not the Satterthwaite distribution. I've never heard of it. So Satterthwaite came up with a correction. Welch and Satterthwaite both did this. So they both get some credit on this. But they said, well, I can end up steering it towards its closest t-distribution. So that's what they end up doing. I want to use the t-distribution. We've used it for this other test where I have equal variances. I want to use a t-distribution. So do you know why they wanted to use a t-distribution? It was easy to table, and tables already existed. So they wanted to steer it towards the closest t-distribution out there. And so they end up doing a moment matching correction or something like that. There's a lot of different derivations, and this approximation has been improved on continuously. There's probably 200 papers written on these corrections. This one's not too bad, especially in this case, where these things are both normal. Works out pretty good. All the other corrections come in for when you change those. Skew the distribution, this thing falls apart, this approximation. Does anybody know what distribution this follows? It's not t. With that degrees of freedom, that's just an approximation. Give you a hint. It's called the Variance-Fisher distribution. So that's what it's called. And it has a whole bunch of parameters. Imagine tabling this. I need to know what these are. So in those cases, I need to know a whole bunch of stuff, and I can't look at a table because that table would fill a book. And so we're talking about this legacy of error that gets passed down to us simply because we used to table things. And so if you're not aware that this case is wildly different from this case, and if you've ever gone to statistical software and tried to do this two-sample t-test, check to see if you did it right. Check to see how big the answers would change if you use this approximation, and I ended up just throwing hats on here, and I didn't change the degrees of freedom, to this thing. I bet they're totally different. So, and that's pretty common. I'll show you in a second. So, anyway, no big culprit here, no culprit here, but this is a really big issue. So let me show you some results real quick. I'll ask you to do some of this on homework, and I'll give you this piece of code. Let's just go through the cases. I wrote this last night. Does anybody have a power plug for a Mac?
Bro, I actually do.
I'll take it. We got 2%, so I want to show you this whole thing.
Weird, right?
Thank you, Anna. So let me just show you what I've got. So I'm just going to be monitoring the type 1 error rate of a process. Somehow that's what frequentists are always protecting, and they say I've got a particular type 1 error rate. That's their alpha. And so I want to see, I just want to monitor what the actual type 1 error rate is in all of these cases. Okay, and I'm going to play around with a couple things. I've got sigma x and sigma y, and I'm just going to set them to different values and see what happens. I can set them to be the same values and see what happens. And I've got a hypothesis that I'm testing, so I'm going to do the corresponding one-tailed test. So I'm going to be testing this, mean x is less than or equal to mean y. And so how I'm going to do that is I'm going to generate data using two normals. And I've got this little shift parameter I call delta. So when delta is 0, then the null hypothesis is true. Okay, so it's true in that case. The null hypothesis, these means are exactly the same when delta is equal to 0. And so the number of times that I reject should be 0.05, according to these tests, if I use the thresholding rule that comes from 0.05 cumulative on one side of the tails. So I'm going to come up with a critical threshold from these distributions, and then I'm going to see how often you're outside of that critical threshold, when you're over it. And that's going to be a rejection. So I'm really using the inversion of the test, the confidence interval sort of thing, instead of computing the p-value. But they're one-to-one. Okay, so we'll leave it here, and I'm just going to be monitoring type 1 error rate. When I change this number, it's checking the type 2 error rate. And the type 2 error rate is a function over delta as I change. So type 2 error rates happen when the distributions have different means, and there's degrees of differentness that I can measure through delta. When you plot all those type 2 error rates as a function of delta, that's called the power curve. Okay. It's also a function of how big the sample sizes are as well. So I can change sample size if I want as well. That has something to do with it. So I end up estimating my two variances. I'm going to check case 1 first. And when I give you this code, I won't have blocks of code that you need to comment. I'll put a conditional statement in here for you. But case 1 is just the variances or no. And so I'm going to use this same distribution that we wrote down right here. And I'm going to end up using the inverted form. So that's what you end up pivoting around to come up with the critical threshold. So the critical threshold is just the norm inverse. This is the quantile function in MATLAB. This would be Q norm in R. And so I'm just going to plug in 0.95. This number is always 1.96. It's really close to that. You can check. But I computed anyway. Oops. Oh, sorry. 1.96 for the point test. So this is the one-sided test. That's the right number. So it's a good thing I did encode this. I know. So, here we go. Constant. I did code this up the first time doing the point test. I wanted to exemplify it to you. But I want you to compare all this to the Bayesian result. In the point test and the Bayesian result, for the Bayesian, I need to spend a couple lectures explaining to you. But for the one-tailed test, it's just integrating over that posterior in that direction. Chase the alternative. So this is the distribution. That's the test statistic. And I'm going to come down and I'm going to check to see if the test statistic is bigger than the critical threshold. And then I'm going to count my rejections. And I'm just going to do this in a loop. And I'm going to asymptotically approximate what is the type 1 error rate. It should be 0.05 because I plugged that in right here. So it should match that number. I want to see how good the approximations are. So let's just run this. Variance Fisher. So I run it and it's 0.0470 for one simulation. How many draws did I do in this? I did 1,000. Let me do it again. 0.0450. Let me do it one more time. 0.0610. Not quite 0.05. What that tells us, if I cranked up this number right here to a bazillion, this would converge to 0.05. So how fast it gets there concerns the efficiency of this test. Okay? How good is the test asymptotically? This isn't even an asymptotic result, but I'd like it to be 0.05 for even small sample size. So there's a little bit of variation in there. So that's typical. Let's see how much variation there is in my whole sampling technique. So I ran this whole test in a loop. so that you can see how much variation there is so you can monitor my Monte Carlo error and know that, did I just show you a real result or did I show you something because of Monte Carlo error? I am doing a Monte Carlo experiment, so I need to tell you how much error there is. So I'm going to run this 100 times. I'm going to plot everything. I'm going to show you the mean and I'm going to show you the standard deviation. So plot Variance Fisher. It's going to run 100 times and show me some stuff about how good can we trust these numbers. So on average, my error rate was 0.0499. So I did 100 times 1,000 samples. So this is based off of 100,000 samples. So that thing is really good. Okay, so I need to run it about 100,000 times to realize that the 0.05s that I'm getting out of here out of my Monte Carlo experiment match theory. So that's how good the normal test works. And there's my standard deviation, 0.07. So I'm pretty good down to the second decimal point. So I feel pretty good about that. So probably would run it just a little bit longer if we could. So this is a known result, and things basically hovered around 0.05, and the true result is 0.05. And so no problems here. This is just a demonstration that what the frequentists are telling you is true is true. Okay, so everything's good right here. So this is my test case. Frequentists do a pretty good job. This was also done off of wildly different variances. So 2 different sigma values and 2 different sample sizes. So let's just check case 2. This is the pooled thing. If I end up pooling, some people do this. They'll run off and they'll pool. And this is a horrible mistake. And people shuffle around their t-test. Which t-test? I don't know how to use a t-test, but there's some t-test out there. And every statistician should be astonished that I'm even going to check this right now. But in Stat 101, I wasn't too clear on which tests I should use and when to use them. So let's just run this thing again. I'm going to run it 100 times so we can see the variation in it. We'll look at my average type 1 error rate. It's supposed to be 0.05, at least if that were a t-distribution. It's not a t-distribution. So this thing right here, I'm using this result with those degrees of freedom. And I'm making a horrendous error by pooling my variances. My actual type 1 error rate is about 0.27. And so rejecting at the 0.05 level is really easy right here. People getting 0.05, this is the real, like I need to look at this critical threshold and blast it way out there to match this thing for this really to be 0.05. And so you would need a p-value, I'm contending, of about 0.27, and you would reject that to really be rejecting at the 0.05 frequency. Why is it all wrong? Because that's not t, and we think it is. So huge repercussion. Let's just do a sanity check and see that maybe they told us the right thing in Stat 101, that if these values were close to each other, let's make them exactly the same, let's see how well it works. And it should be close to 0.05. So we're using the frequentist criterion on the frequentists. Run this 100 times so we get a feeling for our Monte Carlo variation. My type 1 error rate is 0.0498, not too bad. And 0.0067 is my standard deviation. So pretty good. It's doing what it's supposed to. And that level of variation in there is comparable to what we saw using this test. So the asymptotic result is, the result is right if those 2 things are equal. But if they're a little bit off from each other, you can have really weird repercussions. Let's just change this a little bit. Let's let this be 10. See how well we do. So I remember asking these questions, well, what's close? How do you do it? So what does classicists really do? Bless you.
They do the ratio if it's less than 2.
Yeah, so what do they end up doing? Somebody, yeah, so Christina, I think, has the prescription. So what do they teach you? So this has error rate of over 0.08 right here when they were kind of close to each other. So I should be rejecting at the 0.0835 level to have about 5%. And so this kind of explains some of the over-rejection we see. I think also the cherry picking and running off to nonsensical tests has something to do with it. But this can be all over the place depending on what I pick for n. And so both my n's were over 31. But Christina, what does a data analyst do to check which tests they're supposed to use?
So if the ratio is less than 2, they can put
Which ratio?
the ratio of the variance.
The two variances. What statistic does that follow? The ratio of the two variances? It's not Cauchy. It's F. It's an F test. So it's an F distribution, and that particular one, maybe it's special, but you do the F test, and then you check some p-value based off of some condition. You toss that one at the end of the day, and your whole level of uncertainty is supposed to be reflected by your last alpha level that you
Where
use.
does the 2 come from?
F distribution.
From the tables or something?
Yeah, exactly. So it's that's F distributed. That's what I learned when I was an undergrad. So you do all this kind of weird stuff. This is a real problem. And so if you ended up pooling, some people will try to correct this distribution. Welch originally said, correct the other distribution and use this approximation. Let's just check this approximation and see what Welch said. Welch was a pretty reasonable guy, so I don't think he was lying to us. Changes the degrees of freedom, so I'm just going to change the degrees of freedom by computing whatever this weird number is. I'll run this thing and it does pretty good. .05, exactly. A little bit of error in there. So figure 1, and it hovers around .05. So the Welch-Satherway correction is pretty good in these cases. So what I want you to do for your homework, what I'm going to ask is I'm going to ask you to do, after you turn in this next homework, I'm going to ask you to compare the Bayesian one-sided thing implemented as a Gibbs sampler to all of this. I'm going to basically ask you to check the frequentist properties of a Bayesian procedure and see how they compare. The nice thing about the Bayesian procedure is I don't even need to think about it. I don't need to do a pre-test on anything. I'm just going to assume they're different. And I'm going to build things out of the Behrens-Fisher distribution without even knowing it by using a Gibbs sampler. So I think it's okay to not be able to write down the Behrens-Fisher distribution because you've never even heard of it and nobody even uses it in the first place. So my point being is that this pooling activity is a real statistical crime. Sometimes I think the way people use it. Now, Stat 101 teachers around the world are going to come back to me and say, I told my students correctly what to do. And that's fine. So I want to check to see if those students know 5 years later when they're data analysts, if they know what they're doing. Because I think a lot of us would have failed this test. And so done maybe the wrong thing, not known what to do, not known where the statistical crime was. It's in estimating that standard error. The Bayesian, however, doesn't need to think about any of this. So here's what a Bayesian is going to do. We'll have a review session also on Wednesday. So, the Bayesian.
Scott, can I ask a question on the frequentist thinking?
Yes, please.
So is there a way to have like a Q Baron-Fisher instead of just...
Of course, right?
Okay.
So
that would give you the ideal property.
yes, certainly. And you could approximate the inverse CDF. You're not going to be able to invert it. Because you're not going to be able to write down the CDF exactly. You could do an accept-reject thing to sample from it and understand all the properties. You could do this. Yeah, absolutely. So why haven't we? It's a good question. So I don't know. It has a lot to do with what we did yesterday and the day before and then last year and the year before. And people have been inundated with this. But I do think that this is a big culprit that people sometimes don't know. They say they t-tested. They'll say they pooled variances in particular ways. Nobody really knows what happened to the corresponding type 1 error rate. But I would say if you're a frequentist and you don't buy into any of this Bayesian stuff, sometimes you can apply the Bayesian stuff in a frequentist manner. And so But if you're using these more traditional tools, simulate and check their performance on problems that are similar to yours and make sure that what you're reporting and the interpretation is at least accurate. So I think if we would have pooled, we would have made a huge error. Okay, the Bayesian. They've got 2 steps. Step 1, you write down the likelihood. It's pretty easy. So likelihood of all these parameters, I'm going to call it phi x, phi y, mu x, and mu y. There's 4 parameters in my thing that I need to tend with. And then I have all of my data, x and y. And this is pretty easy to write down. I goes from 1 to n, phi x 1/2, e to the minus phi x, xi's minus mu x squared. They're conditionally independent of each other. E to the minus 1/2 yi minus mu y squared. So there's my likelihood. Now I need some priors. Step 2. Phi x is going to be proportional to 1 over phi x. Phi y proportional to 1 over phi y. If you're not sure about your prior choices, you want to see what impact they have on your inference, my solution is easy to you. Go simulate it. See your performance. Make sure that what you're interpreting and reporting is correct. If you need to modify your priors to get there, that's a nice nod. So P mu x proportional to 1, P mu y proportional to 1. I would start there. These standard sort of choices. They have pretty good frequentist properties. I could probably engineer through some math. I could derive what the posterior is and figure out how I need to tune maybe conjugate priors to give me whatever property I'm after. So, or find some other functional form for priors to give me whatever property I'm after in my posterior. So that's what I think priors are supposed to do, is give you a property or reflect your knowledge, depending on which Bayesian you want to be at the time.
Check your likelihood. You need to divide by 2 in the x, and then you need to
Ah,
feed
yeah.
the y in the y1.
Is that it?
And then you need to feed the y in your y.
I can't hear you. Where? Where?
Exponential minus phi.
Oh, this one.
Yes.
Yeah, all that good stuff. The way it's supposed to be written. Thank you. Is that right now? Yeah. Cool. The thing I'm supposed to write down, for sure. So what a Bayesian will do is they'll usually just run a Gibbs sampler. I don't know what distribution that has. Once I multiply these in, I'm not sure. I'm just going to do this. So 4. T goes from 1 to some large number. I'll initialize this thing to begin with. So step 0, initialize. And then I'm just going to update mu x t. I'm going to get it from its distribution, its posterior distribution, given everything else. So what distribution is this?
Normal.
It's going to be a normal. Do you know which one it is? You might need to work it out.
So that would be like x bar and
Yeah.
sigma squared over n.
Yeah, it is that one. Yeah. So it's just the typical one that we always use. So I'll just leave this as a question, but it's some normal. Has to do with x bar. Takes into account what your last iteration on phi was. Maybe I'll just write it down for you. So x bar. One over phi x t minus 1. And right there. So then I would update mu. there? That's supposed to be an x, given everything else. And it's going to be some normal, and you can figure out which one it is. Phi x t is going to be some gamma. I'll let you figure out which one it is. And phi y t is going to be some gamma. In figuring out which ones those are exactly the same problems that we confronted ourselves with for the first couple weeks of class. So this part's not going to tell you much about the y stuff. So this is all normalizing constant, it falls out. All I need to look at is this. And so I know the identities of which came from which component. It's not a mystery to me, so I don't have to do any of that extra Gibbs sampling to learn which x's and y's came from the components. They're labeled, we know.
And then maybe you record μx minus μy.
Yeah, exactly. So I do this, and then maybe at the end of the day, I draw you a histogram of μx minus μy. So store everything and analyze it for convergence. This will converge quickly, just like the Gibbs sampler you did for homework. But analyze everything convergence and analyze μx t's minus mu y t's. So I could call this something, I could call it delta t. Say that thing is equal to that, and I'm going to end up coming up with a histogram representation of this. And so if I wanted to check to see if they were the same or something like this, I'd be comparing these against 0. So if I saw a 0 over here, then I'd probably think they're different. Now what I haven't told you about is checking exactly 0. And there's a whole Bayesian methodology for it. But doing the one-sided test, this is a pretty simple exercise. So what I'd like you to do is run this Gibbs sampler. If you're already done with the homework, I will be issuing this homework soon, is basically do this and compare it to the other tests. So the 3 cases that we've seen so far. And I'll probably ask it to be fairly open-minded, where you come up with what you want to report to me. What do you think is important to report? I think getting into that mindset of what are the important aspects to report in the simulation study is kind of the art of it all. You can't report everything, so you want to report the meaningful things in kind of a small amount of space. So you don't want to walk in, here's 70 pages worth of plots. I won't be impressed. So people come to me with that, aren't you impressed? I printed out all these, no, because I can't read through them. Anyway, that's the name of the game on the Variance-Fisher problem. So it's a big problem, but for the Bayesian, I don't think it's too much of a heartache. You just run your Gibbs sampler. Point null test is more contentious. It's contentious also for a Bayesian, but at least a Bayesian is telling you what they believe. And so I'm going to tell you about that next time, but it's going to have to do with point mass priors. So that's where we're going to pick up next time. I'll tell you about Bayes factors, point mass mixture priors, and then eventually I'll show you what the Gibbs sampling scheme is for it. One more. There was a question during class, I think you had asked it, you had asked Sierra, when I end up making the parameters exactly the same and I deal with case 2, do I have 2 priors or do I have 1? So do I have a prior on, I used to have a prior on phi x, I used to have a prior on phi y, but in the case where I want to make them the same, you only have 1 prior because you only have 1 parameter. Now, you might think about, how do I run this in an MCMC if I wanted to jump back and forth between those 2 cases and figure out, do I only have 1 parameter or do I have 2? Could I do this in an MCMC fashion? And I can't just use any old ratio to compare them. I can't take the likelihoods or the posteriors of both of those to compare them because one lives in a 4-dimensional space. When I have both of the phis, when I have the phis different, and it lives in a restricted space, a three-dimensional space, when phi x is phi y. So you can't compare those directly to each other. How do we normally compare two distributions with two different dimensionalities? We just need this extra piece. If I want to transform from a two-dimensional space to a one-dimensional space, I can't just do it directly. Yeah, you have to do something else too. What's that? So I need to at least introduce, I have to anti-marginalize. So I need to introduce a new random variable. So if I want to compare them. And so I need an auxiliary variable. So remember when you do a problem like I've got distribution of x and distribution of y, and I want distribution of x plus y? I couldn't have done that directly. I needed to probably come up with another auxiliary variable, x minus y, so I can set up a bijection between the two spaces. And so you can build these bijections into your samplers. And I could check to see if I thought phi x was phi y. And that's called reversible jump. So that came out in the early 90s, I think 1995 by Peter Green, and I'm going to be telling you all about it. There's a little bit of a rub because that bijection sets up your proposal. And if you set it up wrong, you could have a nightmarish MCMC, and I'll show you some corrections to that and how to run these things. But your question is a good question. You can't compare a two-dimensional space to a one-dimensional space. You can't have two priors on there. So you only need one prior when there's a parameter. One parameter, one prior. But I'll teach you how to exploit that dimensionality matching in MCMC in future weeks. That's it for now, guys. Thanks so much.